Hello YouTube. In this video we're going to examine the views of Paul Feyerabend, particularly his book Against Method. Feyerabend is an extremely controversial figure in philosophy of science. Among other things, he was once branded the worst enemy of science, which is something of an exaggeration, but he definitely expressed some quite radical and challenging ideas. And he became one of the main inspirations in the postmodernist and relativist movements. He seemed at times quite critical of science, quite critical of the idea of scientific progress. Of course, Thomas Kuhn was also a big influence on these movements, but Kuhn himself wasn't really very happy about that. He felt that the more extreme relativists had misinterpreted his views. Feyerabend, on the other hand, embraced it. Now, it's worth bearing in mind that Feyerabend may not have been entirely serious about everything he says in his books. To some extent, he's trying to be contrarian. He wants to play the devil's advocate in some ways in order to prompt critical discussion. But I think that the main claims he makes, he does genuinely believe. So, you know, I think most of what we're going to talk about here, it does represent his genuine position. As a bit of background, Feyerabend was heavily influenced by John Stuart Mill, particularly Mill's On Liberty. In this essay, as you're probably aware, Mill passionately defended freedom of expression. He held that all views, all theories, no matter how ridiculous or repugnant, should be given a fair hearing. We should allow people to express them. There are several problems with silencing an opinion, even opinion that's obviously false or obviously morally evil. So first of all, Mill says that the opinion, for all we know, might well contain a grain of truth. So, for instance, Hitler's Mein Kampf. Well, we shouldn't ban that. For one reason, because even though on the whole it's obviously awful, there may well be some parts of it that contain insights. So I've never read Mein Kampf, but I looked it up on Wikipedia just before doing this, and here's a quote describing part of the book. It says, Hitler announced that he wanted to completely destroy the parliamentary system, believing it to be corrupt in principle, as those who reach power are inherent opportunists. So, yes, the anti-Semitism, the racism, that's obviously awful, but maybe there's something to learn from Hitler's criticism of opportunism in the parliamentary system. I don't know. I haven't read it, but you know, you can see the point here. Even the most terrible people may well have some insights. But perhaps a more interesting point raised by Mill is that even if the opinion that you silence is wholly false, if you silence your opposition, then the accepted opinion will become held as a prejudice, a dogma, without any rational grounds. It's worthwhile to allow racists to speak so that the people who oppose racism can properly understand their opponents and properly criticise them. By engaging in the debate with racists, your own opposition to them becomes stronger. You gain a better rational grounding for your views, because you're forced to think through the arguments for your position rationally, you know, rather than just reeling off a few anti-racist slogans. I mean, I'm sure you've met people who are against racism. I mean, most people are against racism, right? But they're against it in a sort of purely emotional way. If you talk to them about it, they haven't really thought about it critically. And that's not something we should encourage. We should want people to hold their views with good rational grounds. Obviously, racism is an extreme case, but this is true in general. The road to truth, according to Mill, is proliferation of different views competing in the marketplace of ideas. And notice that this isn't just a legal argument, right? It's not an argument for the absence of censorship. We often define free expression in purely legal terms, but Mill's arguments can be extended further than this. It seems that what this is saying is we should actively encourage different perspectives and different views and different theories. In cases where everybody is in agreement, we should intentionally cultivate disagreement, because it's only by pitting opinions against each other and allowing them to develop to their best extent that we can judge matters appropriately. It's probably useful to see Feyerabend's views in this light. Feyerabend held that there was great value in being contrarian and expressing unpopular views, and we will come back to Mill a bit later, but I just wanted to talk about that here because I think it's a useful way to frame Feyerabend's ideas. Anyway, Feyerabend's central claim is that there is no universal scientific method. In this respect, he says science is a kind of anarchistic enterprise. Scientists routinely violate the methodological rules that philosophers think are important, and this is a very good thing because progress requires that you sometimes break the rules. If scientists adhered to some strict universal method, scientific progress would be completely crippled. And this is the case no matter how you define progress. Obviously, different people will have different ideas about what constitutes progress. Feyerabend says, no matter what your view on scientific progress is, it will sometimes be necessary to break the rules. So what's Feyerabend's argument for this? Well, his basic claim is that for any methodological rule you care to come up with, you will be able to find various cases throughout the history of science where that rule was broken to the benefit of science. So if you are what he calls a rationalist, and by rationalist he means somebody who believes that there are universal methods for arriving at the truth, if you're a rationalist, the only principle that you'll be able to defend, the only principle that works in all circumstances is anything goes. Any principle that is more substantial than this will rule that much of the best science was actually not science. And so this is the only principle you're going to be able to defend. Now, it can be easy to misinterpret Feyerabend here. Feyerabend is not arguing that we should adopt the principle anything goes. Indeed, in a later work, he describes this principle as empty, useless, and pretty ridiculous. Rather, what he's doing is giving a reductio argument. His point is that if we approach science from a rationalist perspective, if we assume that there is a universal scientific method, then we will find that the only method that squares with the historical facts is anything goes. Obviously, it's absurd to suggest that anything goes is the scientific method. So this shows us that this whole rationalist project of trying to specify a scientific method is just a mistake. As his book, as the title of his book says, he's against method, including this rather silly method here. So Feyerabend isn't saying that a scientist can do whatever she wants to do and expect that this will always lead to progress. Scientists do follow methods, but the point is that the methods will be different in different circumstances, and occasionally some genius innovator will come along who abandons the accepted methods and who thereby makes progress. Now, insofar as Feyerabend objects to any methodology, he can appeal to arguments that we've already discussed in other videos. So, against inductivist theories, Feyerabend argues that it's not necessarily acceptable to infer theories from evidence because evidence is contaminated by theory. Recall the points about theory-ladenness of observation in the video on incommensurability. Against the falsificationists, he can argue, as Lakatos did, that all theories face anomalies, and in the last video we saw various criticisms of Lakatos. Kuhn, of course, also downplays method. But Feyerabend strongly objected to Kuhn's notion of normal science. In general, he claims that normal science doesn't exist, and it would be bad if it did exist, right? So this is Feyerabend emphasizes the value of competition, and we've already seen from our discussion of Lakatos that very often scientists don't adopt a single monolithic paradigm. They will try to develop competing theories, and that's something that Feyerabend thinks is very important. Okay, the central part of Feyerabend's argument is a rather long discussion of Galileo, particularly Galileo's defense of heliocentrism, which is the view that the Earth orbits the Sun, first proposed by Copernicus. We can't go through all of the things that Feyerabend discusses in his book, but I will examine some of what I think are the more important comments. So first of all, it's worth laying out the argument explicitly, and so this is how I'm sort of reconstructing Feyerabend's argument. He doesn't put it like this explicitly. His book is a bit more impressionistic, but here's basically how I think it goes. So premise one, if there is a universal scientific method, then it will be exhibited, at least most of the time, in the behaviour of great scientists. So the thought here is that we treat certain people as central figures in the development of science, and we want our account of the scientific method to be compatible with what they did. We can't rule those people as being irrational. And that's why Feyerabend is going to compare suggested scientific methods with the behaviour of great scientists. There's obviously no need to look at bad scientists. We wouldn't expect them to follow proper scientific method anyway, and even good scientists would sometimes make mistakes. But if there is a universal scientific method, surely it should be practiced by the great scientists. Okay, premise 2. Galileo was a great scientist. That seems pretty plausible. He was one of the heroes of the scientific revolution, so he's one of the scientists that we can't rule that he was irrational, right? If anybody was a rational scientist who followed the method, it should be Galileo. Premise 3, every plausible method so far suggested was violated by Galileo. Conclusion, there is no universal scientific method. There is no method that applies in all circumstances. Scientists are much more creative and opportunistic than this search for a scientific method suggests. Of course, we might still hold out hope that some philosopher will come up with a method that wasn't violated by Galileo, but Feyerabend thinks that a close attention to Galileo's work makes this extremely unlikely. Galileo relied on rhetorical tricks and propaganda in order to defend the heliocentric system. The arguments and the evidence were far weaker than we might expect. So a first point here is that heliocentrism was inconsistent with well-accepted theories of Galileo's day. Geocentrism, the view that the Earth is the fixed centre of the universe, was just one part of a whole metaphysics that had been proposed by Aristotle and then developed over hundreds of years by the medieval Christian philosophers. And this sort of Aristotelian worldview was really a very powerful and well-confirmed system. So in the Aristotelian worldview, the cosmos is divided into many spheres, with the Earth fixed at the centre. Now, there are the terrestrial spheres, which are places of corruption and change, while the celestial spheres are perfect and unchanging. Terrestrial spheres contain earth, fire, air and water as basic elements. So all terrestrial objects are made of combinations of these elements. Objects in the celestial sphere are made of an element called ether. So this is the moon, the sun, stars and planets. These are all made of ether, and that's displayed in this diagram here. We have the Earth here at the centre of the universe, and then here are all the celestial spheres up to the fixed stars. Now, Aristotle explained gravity by claiming that all objects have a natural place, and the elements will tend to move towards this natural place. An element that is unopposed by any obstacle or force will move to its natural place, and then it will remain there at rest, unless, of course, you move it out again. Unless you apply a force to it and move it out. The heaviest element is Earth, so Earth sinks to the centre. The natural place of Earth is at the centre of the universe. The natural place of water is in a concentric circle around the Earth, concentric sphere around the Earth. Air is in a sphere around the water, and fire is in a sphere around the air. And objects will move depending on the proportion of the elements they contain. So when a stone, for example, is primarily made of earth, and so that's why when you put a stone in water, it falls down. All motion is explained in terms of the properties of the elements and their natural place. And I won't go into details here, but this same metaphysical view was presupposed in biology, in psychology, in medicine, in theories of causation and so on. It was a very expansive worldview, and Aristotle and his successors had applied it to a variety of different fields. Now it's clear that heliocentrism is inconsistent with this theory. Heliocentrism eliminates the notion of a natural place, and that means that a new theory of motion is required. Now, of course, Galileo provides this. On Galileo's theory, very briefly, all natural motion is circular. So just like how the moon orbits the Earth in, well, he thought it was a circle. He thought the planets orbited the sun in a circle. Any deviations from circular motion are explained by intervening forces. Furthermore, a very important concept in Galileo's theory is the relativity of motion, which explains why we don't feel the motion of the Earth around the sun. Now, today we see Galileo as providing a substantial improvement on the Aristotelian theory. But in fact, Galileo radically reduces the content and the scope of physics. Aristotelian physics was a general theory of all kinds of change. It aimed to explain locomotion, so that the kind of push and pull on objects. It aimed to explain qualitative change, generation and corruption in biology, birth and death and degradation in biology. It could even be extended to explain mental processes, such as the transmission of knowledge from teacher to pupil, and so on. The principles of Aristotelian physics can be applied to a whole variety of different domains. Galilean physics, on the other hand, concerned only locomotion. It concerned only the push and pull and forces between physical objects. Galileo made no attempt to extend this to the many topics that were treated by Aristotelian physics. And actually that was the case for the atomists in general. Going way back to Democritus, they focused on causes and effects between atoms, and then they just assumed without demonstration that this could be extended to explain all other things. Anyway, heliocentrism was refuted by the dominant physical theory at the time, deriving from Aristotle. Galileo developed a new theory, but there wasn't really any good reason to accept this theory. It wasn't nearly as powerful as the earlier Aristotelian theory. The traditional picture that we have of science is that new theories should display increasing empirical content, as Lakatos would say, or increasing puzzle-solving power, as Kuhn might say, or increasing explanatory power, or whatever. In this sense, there's a kind of progress. But Feyerabend says this is just wrong. New theories are often extremely impoverished relative to the old ones. The Aristotelian system was a comprehensive theory of the world that had been worked out in detail over many centuries. Galileo's physics applied only to a sort of narrow domain within astronomy and a few associated sciences. Now you might say, well, okay, but surely the situation is that heliocentrism was established by observations, especially the observations that had been made through the telescope, which was an instrument first used in astronomy by Galileo. Having established heliocentrism, it was necessary to develop a physical theory compatible with it. But in fact, heliocentrism was refuted by observation, at least according to Feyerabend. And Feyerabend thinks that Galileo's responses to this refutation similarly violate standard methodologies. So one of the most serious problems for the heliocentric theory was that as it entails that as the planets move around their orbits, we will view those planets at different distances. And Mars, for example, should appear 60 times brighter at its closest than at its most distant. Venus should appear 40 times brighter at its closest. Looking at the planets with the naked eye, you can see that they don't change. We just don't observe these differences in brightness. Galileo's response to this is to appeal to the telescope. He says if you observe the planets through the telescope, you can see the changes in their size. The telescope is superior to unaided vision and therefore provides good inductive support for heliocentrism. But the trouble with this response is that there was no good reason at all to believe that telescopes were superior or even equal to unaided vision. In fact, there were very good reasons to be distrustful of the telescope, to think that it wasn't a reliable instrument. A first point here is, recall the Aristotelian background theory of Galileo's day. On this theory, celestial objects are made of ether, which is a completely different material to terrestrial objects. And these celestial objects obey different laws. So even if the telescope reliably depicted terrestrial objects, there was no reason to expect it to work for objects in the celestial spheres. And furthermore, Galileo never provided an alternative theory of optics and matter that would render the telescope reliable. So no scientist who accepted Aristotelian physics should have found the telescope even remotely persuasive. The second problem is that it turns out that even for terrestrial objects, telescopic images were often severely distorted. They had coloured fringes or blurring or doubling. Now, using the telescope for terrestrial observation, that's not really a problem, because we all have direct acquaintance with terrestrial objects, so we're able to tell when what we're seeing is illusory. When we see some weird pattern of colour around a ship, we know it's an illusion because we know what ships are supposed to look like. But when we turn the telescope to the skies, we have no way of telling whether what we're seeing is real or an illusion, whether what we're seeing is the object as it is, or is due to a contribution from the telescope. And the actual results that were obtained from the telescope provided very good reason to be sceptical. So observing the moon, for example, Galileo described massive jutting features in its interior, mountains and chasms, while the edge of the moon appeared perfectly circular, without any protuberances. Galileo described the edge of the moon as sharply defined, as if marked out with a pair of compasses. And that's despite the fact that the exact location of the edge of the moon was known to change due to libration. So we don't always see exactly the same face of the moon all the time. It sort of wobbles ever so slightly. So very strange that Galileo would report seeing mountains and chasms in the interior, and yet the edge is perfectly straight. That seems inconsistent. Furthermore, Galileo's own drawings of the moon had inconsistencies with what we could observe with the naked eye. So here's one of Galileo's drawings, and it shows this very prominent centre crater. This crater is large enough that we should be able to see it with the naked eye if it was there, but it isn't there. You can just go and look at the moon outside and you'll see that no such crater exists. Or you can look at photographs of the moon online. There just isn't that crater. I think there is a crater sort of in the same area, but it's not nearly as big as Galileo draws it. So it's sort of obvious that his telescope isn't that reliable. Finally, another odd result, at least for the people of Galileo's time, is that while the telescope magnified the moon and it magnified the planets, it had no effect on the stars. So lots of very strange results there. And all of this was made much worse by the fact that different people using the telescope often gave different reports. Many of Galileo's contemporaries argued that the telescope was adequate for terrestrial phenomena but couldn't be trusted when observing the skies. Shortly after Galileo reported discovering Jupiter's moons, he took his telescope to Giovanni Maggini and 24 university professors to confirm his discoveries. And none of them were able to see the moons clearly. They all felt that the telescope was quite deceptive when turned to the skies. Another great example of this, actually, which Feyerabend doesn't mention, is the case of Saturn's rings. When Galileo turned his telescope to Saturn in 1610, he realised there was something unusual about it, but he didn't realise it had rings. Numerous other astronomers tried to figure it out, and they all saw it in different ways. Here are just some of the different ways that Saturn was seen, and if you look it up, you'll find that there were actually many more. It was seen in all sorts of ways. It was only in the mid-1600s, after far more powerful telescopes had been constructed, that the ring theory was worked out. So let's sort of sum all of this up. The overall situation is that heliocentrism was incompatible with well-established theories of motion deriving from Aristotle. Galileo resolved this by developing a new theory of motion, but this new theory was much weaker than the Aristotelian predecessor. Furthermore, heliocentrism was directly refuted by simple observations of the apparent brightness of Mars and Venus. Galileo solved this problem by using the telescope, but this required assuming that the telescope was accurate, and that itself was also refuted. So there were two refuted views: heliocentrism on the one hand, and on the other hand the view that telescopes provide accurate images of the night sky. Galileo was able to show that these two refuted views were mutually supportive. And in that way he tried to defend the theory. But of course that couldn't possibly be convincing to any scientist at the time who obeyed any of the rational methods that have been endorsed by philosophers.